Hello, my name is Mason Sharp, and this is my project on parametric graphs. Before we get into the meat of everything, let me first go over some slides to give some information. So, what are parametric graphs? Parametric graphs are a way of visualizing parametric equations through the method of plotting points individually. They can be used to show how the position of something changes over time, and it's represented by an x-y pair, with the time being represented by the variable t. We can see in this graph here, we have a bunch of points with t is equal to 0, 1, 2, 3, and so on, just infinitely up and infinitely down, and a set of points that are associated with that time. And as the time goes up, you can see that this arrow points towards the direction that the equation is going in, and here it forms a parabola. And moving on, here we have our first example, graphing a pair of parametric equations. So let's say we need to sketch a graph of the following parametric equations. X of t equals t minus 3, y of t equals 4 plus t squared. The first step in graphing this equation is to create a 3-column table, as you can see here. The first column represents t, and we can put in any numbers we want here. Let's just put in every whole number from -3 to 3 to keep things simple. So as you can see here, -3 to 3. The next column holds the result of the x equation with the given t, and the final column holds the result of the y equation with the given t. Once every spot on the table is filled up, we can begin graphing. So we can see x of t pretty much just means like the x position that will be in the xy pair on the graph. So here we have t is -3. If we plug in -3 for t, -3 minus 3 is 6. We get our -6. We get put -6 here, and then same for the y. If we plug in -3, -3 squared would be 9, and then you do 4 plus 9, and you get 13. And you just do that for every t value that you're graphing up to. And now we can begin graphing. I could just show an image of a graph to show off the points, but I feel like that doesn't do it justice enough. So what I set out to do is I set out to create a simulation that can be used to show exactly how the graph changes over time. So if we begin our simulation here, and here we have it. This will look a little confusing at first for sure, but pretty much all you need to know is we have our x equation in the top left, our y equation below it. We have our range, which we saw earlier, how we plotted from -3 to 3. This is a way of showing that. And then here we have t. Pretty much what I can do is you can see as I enable terms, it shows up for x. If I change it to y, then now I'm editing the y term. And what I can pretty much just do, I can set this to t, which means that now it's t instead of a number. And then like I can add 3, then I can go to like term 2. I can have an exponent, so I could have t squared, and then I can press tab to hide all of that stuff. And then you can see this graph I can move around in. If I press space, you can see t is doing its thing. If I move up, you can see exactly how it changes over time. And I can press Control to reset it. And I can even reverse its direction with pressing O. And I can pretty much just see exactly how I want it to. Exactly where it is over time. Now there are some things you may be confused about, like what each of these squares represent. If I press escape, we can see the settings. Simulation speed is just how fast it goes, so I can change it to 2 if I want it to be twice as fast. T minimum and T maximum, that's just what you see in the numbers up here. If I wanted to do it to 2 and 2, then you can see it goes from -2 to 2. And then our scale, the scale is just what each square represents. So right now, each square is 1 unit of length, but if I change it to 5, now each square is 5 units of length. So now if I press play, you can see that it's in a lot smaller of an area and it goes by twice as fast. So that's how that works. And really, the sky is the limit here with this simulation. I wanted to make sure that you could do pretty much anything you want. So this could be helpful for like problems if you are struggling to visualize how a problem is laid out. It has support for cosine and sine, for t for time, but also for e, which is the constant, 2.7, etc. And then you can have an exponent, which is also can be t and e and can be multiplied by a certain value. But yeah, I'll get more into the graph as I go along. But for now, let's go on to our next slide. And here's our next example, graphing a pair of trigonometric parametric equations. It's kind of a mouthful. If, let's say, we want to sketch the graph of these parametric equations, x equals 4 cosine of t, and y equals 2 sine of t. So you can see here, this isn't in the format we had before of t of x and t of y. You can see here that it's not in the format that we had before of x of t and y of t. But functionally, they're very similar, so you don't really have to worry about it too much. As you can see here, solving this problem is very similar to what we did before. Create the 3-column table, as we've done, except make sure to use angles with known sine and cosine values for the t values so that you can solve them easier. So as you can see, instead of just doing -3, 2, 1, and so on, I have 0, pi over 6, pi over 3, pi over 2, and so on, just to make it easier to plug in to cosine so that we don't get funky decimal numbers. And yeah, then we just plug in t for the other columns. So for 0, 4 cosine of 0, this is 1, so 4 times 1 is 4. This is 0, so that's 0. And then just the same for all the other ones. Fairly simple. But now that we have our simulation, we can actually see what this will look like. So let's open up the editor. So let's see if I remember what it was. It was 4 times cosine of t, 4 times the cosine of t, and then our other one was 2 sine of t. 2 times the sine of t. Perfect. Let me make the scale back to 1. And let's just do this. Let's just start at 0. Maybe go to 3. And let's see it in action. And as you can see here, it didn't get all the way. So let's increase t to, let's say, 12. Start it again. You can see here, as it goes along its path, it makes a circle. And it just keeps going around in a circle forever. But yeah, we have an oval, more specifically, a horizontal. And you can see how that's reflected. The x, here the 4 is bigger, which means that it's going to be horizontal. If the y was bigger, then it would be vertical. Now that we have the simple stuff out of the way, let's move on to a real-life example. Here, example 3, using parametric equations to describe the motion of a cannonball. Here, a cannonball is fired from a cannon at a straight 0-degree angle, 50 feet above a cliff at 200 feet per second. How far does the cannonball go before touching the ground? Well, the first thing we must do is turn this into parametric equations, like with before. So for x, that's simply just going to be the velocity times the cosine of theta, because it's going horizontally, times t. And since the angle is just 0 degrees, it's going straight forward, then cosine of theta is equal to 1. And we can just remove it because it's just multiplying by 1. And we can get our velocity from here. We can see at 200 feet per second. When we plug that in, we get x equals 200t. If we want to get our y parametric equation, it's going to be a bit more complicated because it's a projectile motion problem, and we have to take gravity into account. The effect of gravity is represented by -1/2 gt squared. And g is just the gravitational constant, which is 32 feet per second squared. And this will represent kind of the acceleration of the object as it falls downwards. So for the y equation, we can represent it as what we had here, -1/2 gt squared, plus the velocity times the sine of theta, plus the height. And again, since theta is 0, the sine of theta is also 0. And since we're multiplying velocity by 0, that'll become 0, and we can just remove this. So once we do that, and we solve this, which we have g is 32 feet per second squared, and then times that by -1/2 to get 16. So you have simply -16 times t squared plus 50. And with the 50 being the height, which is seen here at 50 feet above the cliff. So now, in order to figure out how far the cannonball went, the first thing we need to do is figure out how long it was in the air. We're going to do this before graphing. So to do this, we're simply just going to let y equal to 0 and then solve for t in this equation here. So it would be 0 equals -16 t squared plus 50. So then in this case, you would subtract 50 and then divide it by -16 and then take the square root. And if you do all of that math, then you will get around about 1.767 seconds. That's how long it was in the air. So now all we need to do for our final step is to plug in 1.767 for t in the x equation, and that'll give us our final answer. If you just 1.7 whatever times 200, then you will get 353.4. And that is our final answer. And of course, we can represent this in our little simulation. And all right, let's start the simulation. So start it here. Starts at 0, and this thicker line represents the ground. So we can already stop it here. But that might have even been too fast. Let's bring it down to 0.25. That sounds about right. Start it over again. Let's try and pause it right when it hits the floor. So it's going. It's accelerating down at an exponential rate because of gravity. Bam, right about there. And would you look at that? T equals 1.78. If you look at our thing, our time for when it touched the ground was 1.76. Extremely close. And that is a surefire way of knowing that we did our math correctly. And if we do the math here on where exactly this is, each square is 50. So it'd be 5, 10, 15, 20, 25, 30, 35. It's a little bit more. So this is around 360 hours. And again, as you can see, 353. So our graph is correct. And this is the way to represent it. But you can see how this simulation can help people out to understand parametric equations and parametric graphs. To end this off, let's see the capabilities of what the simulation can really do. Let's go to X. Let's just put in some crazy stuff. Let's see what the simulation has for us. Wow. Look at that. It's like a boomerang type shape. This is kind of cool, kind of like a crescent moon. And you can see exactly how it's made. It starts up here over at 0, 3. It goes all the way over to, I believe that's 6. Yes, 6, 0. It goes down to the -3 on the Y. Then it goes the X. On its way back, it comes over to 4. This is probably because of this. There's a lot you can decipher because of the new functionality. And this functionality isn't something that you can find on like Desmos or any other program that I know of. So yeah, I'm very happy with how this turned out. But I believe that is about all. Here's the bibliography. Use the graphing calculator for help. The Unity game engine is what I made all of this on. And the Precalculus book. And yes, thank you so much for watching. And I hope you learned something new.